Hey everybody, Mr. Piercy here, coming back for part two of our inductive reasoning lesson. And what we talked about in the first portion of this instruction was what inductive reasoning is. And we established that inductive reasoning is really simply it's something that we look at to establish a pattern. And from that pattern that we observe, we can then make a statement based on that pattern, which is known as a conjecture. Well, moving on, what we're going to be using it for is not just what we saw in our previous video, where we were folding a piece of paper in half, building a table, and then studying the table to determine what type of algebraic relationship did it have. There are a lot of sequences that will do that, meaning that we will look at it to see how is it changing, determine is it linear, quadratic, or exponential, and then can we write the rule for it based on our statements? But here is a perfect example, a very typical kind of example of a sequence that has absolutely nothing to do with algebra in any way, shape, or form. It is simply a sequence of shapes. And now from the shapes, can we determine how is it changing? Well, we have polygons inscribed inside of a circle, and we start with a three-sided polygon, four-sided polygon, a five-sided polygon. Ooh, that was a bad 5 even for my handwriting. 5. And so the next two should be a 6 and a 7-sided polygon. And I always ask this question in class. Most students for the 6-sided polygon have no problem saying, oh, that is a hexagon. But the 7-sided polygon, that is a septagon. Not everybody knows that one, and a lot of people want to call it a heptagon, but it is a septagon. So those are the next two figures in the pattern there. And moving on, we have a numerical pattern. See how they're changing. So writing out the next two numbers in the sequence for each one, I want you to pause the video when you're ready and figure out, well, what are the next two sets of numbers in the pattern? And then when you're ready, write using complete sentences, well, how's the pattern changing? Okay, so why don't you go ahead and pause the video and write out the numbers, write your sentences, and when you're ready, press start again and see how we're going, or press play again. Okay, so I'm going to, again, assume, unfortunately, that I hate having to assume, but I'm going to assume that you're doing what I'm asking you to do, and you're saying, okay, well, how are things changing in figure A? Well, in figure A, from one term to the next, we're simply multiplying by 3 each time. So if I said 81 times 3, my next number in the sequence would be 243. And the next number after that, multiply that one by 3, and I would have 729. So there's those two. That is, and let's see, let's go blue. The next sequence, each term seems to be decreasing by 5 each time, so we would have 25 and then 20 respectively. And the statements that I have here, you can say that they are multiplying by 3, which is what I did, but they're also, we can say that we're taking it and raising it to the third power, or we're saying 3 and we're taking that to the certain power. So if you're looking at the sequence of the first one, if we made it as a quick t-chart, sideways t, where this is x and this is y, well, when x is 1, y is 3. When x is 2, y is 9. When x is 3, y is 27. When x is 4, y is 20 or 81. Well, basically what we're doing is we're taking whatever that term number is, the 1, the 2, the 3, and the 4, and we're putting that in the exponent spot of the third power. So that's how we could write an expression for it. If you didn't come up with the expression, that's fine, as long as you recognize, well, we're multiplying it by 3 each time. But the expression, the rule is, well, what if I asked you, well, what would the, I don't know, the 30th term be? What number would it produce? Well, you'd have to really have the rule y is equal to 3 to the n power, or y is equal to 3 to the x power, so that way you can figure out how much that's going to be. And the next one here, the sequence is changing by we're taking 5 from the preceding term each time, and that would give us the expression y is equal to negative 5n plus 50 as a rule. Okay, so moving on. These are numerical patterns. These are very typical things that you could expect to see. And if it's a numerical pattern, a lot of times we're going to be able to apply some kind of function to it. So we had another exponential function and a linear function. So just keep that in mind as you're going through these types of problems, that maybe you'll be asked to write, well, what is the expression for it. Now here, what we're trying to do is we're going to now see, can we figure out what a conjecture would be based off of a pattern. Now here, this is what I want you guys to pay attention to. The statement right here that says, what conjecture can you make about the sum of even numbers? That could very well be a quiz question or a test question, and that's all you get, just that question. What conjecture can you make about the sum of the first or of even numbers? Well, what we need to do is, if that's all they're giving us, we need to figure out a way to organize or model our information. Because if we can't see a pattern, we have to be able to create in some way a pattern that we can actually look at, and from there be able to say, okay, well, now I can see how the pattern is changing, so now I can write a conjecture over it. So what I'm doing is I've decided I'm going to create a table, and I'm going to look at the number of terms and see, well, how are they changing each time. So the first term that I have is the first even number, which is 2. Well, since that's the only even number that I have, at that point, I don't have anything to add to it, so the sum of 2 is just 2. Moving on to the next term in the sequence is, I would say, well, 2 plus 4. That would be the sum of the first 2 even numbers, which gives me a 6. And looking at the next one, I would say 2 plus 4 plus 6, had the next even number then, and I get 12. Okay, well, next here, well, I would say 2 plus 4 plus 6 plus 8, and that would give me overall 20. Now, the reason why I've included, and I'm change my width here because I'm looking a little wide in that little tiny box. This last portion of the column, for the sum column, that is where I'm really looking to see, well, that's really where I'm looking to see what the pattern is going to be. Because it wasn't something that was just coming apparently, it wasn't just jumping off the page at me as far as, well, how are the numbers changing? Because if I look at the numbers from 2 to 4 or from 2 to 6, it's increasing by 2. And if I look at the next one where I go from 6 to 12, it's increasing by 6, and then it increases by 8. So it's not having a constant rate of change, so it's not a linear expression. But how else could I look at it? Well, if I continued, if I really did make these out and compared to it and say, well, if it's not linear because the first differences aren't constant, what would the second differences be? And maybe that would give me a clue. So I'm really looking to see, since the numbers themselves here, these values aren't super really just saying, hey, there's my pattern. I wanted to say, well, how could I come up with another way of getting that? And that's where the multiplication process on the final right side of the column comes into play. Here, the first number that I have, that is my term number. And the second number in the column for the multiplication here, that is my term number, that's my term number plus 1. And it seems like that is working out pretty well. Because if I say 4 times 5, that'll also give me a 20. So by looking at the information in a table, I'm giving myself some kind of an organization here. I can see that my conjecture is going to be to find the sum of even numbers I take whatever the term number is and I multiply it to the term number plus 1. So when I apply that, to the first 30 even numbers to see what the sum is, here is the math equivalent of the statement that I was just saying. To find the sum of the first, or to find the sum of even numbers, I take the term number and I multiply it by the term number plus 1. So that's where the sum is, n times n plus 1. And to do it for the first 30 even numbers, well, I just substitute 30 for n, and 30 times 31 gives me a sum of 930. Now, what I would like you guys to do is take that and see, can you apply it to something else. So on the bottom part of this paper here, now you guys have another statement. What conjecture can you make about the sum of odd numbers? So what I want you to do is pause the video and try organizing the information in some way so that way you can see a pattern develop. From the pattern, make a statement, and then determine what would be the sum of the first 30 odd numbers. So when you're ready, push play, and I'll be here when you come back. Okay, I am going to assume that you've pushed, that you've paused, you've done what I've asked you to do, and so now you can see how I'm going to work this out. Well, here's a table that I'm kind of putting together. It doesn't look quite as nice as the one that I typed up, but we're going to say the term numbers and the sum of those numbers. And again, when I wrote them out, well, the first odd number was 1, so the sum of 1 and nothing is just 1. 2, my second term, would be the first two odd numbers, which would be 1 and 3, and so that gave me a 4. And then for the third one, the first three odd numbers, 1, 3, and 5, gives me a sum of 9. And then for the fourth one, 1 plus 3 plus 5 plus 9. And so that's going to give you 16, which would be the same thing as saying 4 times 4. So the pattern that I'm seeing, again, in the numbers themselves, in the sums, 1, 4, 9, 16, I can see it increases by 3, that it increases by 5, that it increases by 7. And so it's definitely not a linear pattern. So how else is it changing? Well, looking at, since the linear pattern doesn't work, now I want to look to see, is there another way that I can get those? And I can take the term number and square it, and that would also give me the sum of those numbers. And so that's how I wrote my conjecture. I said this, so really we should probably say the sum of odd numbers can be found by taking the term number and squaring it. So I'm amending it a little bit for this case and saying the sum of the first, oops, didn't mean to do that. The sum of the first 30 numbers, odd numbers, can be found by taking, again, the term number and squaring it. So the first 30 odd numbers would have a sum of 900. Now I've already explained a couple of times that it's definitely not linear. The first terms, or the first differences, are not constant, so that doesn't work. So let me look here. If I said my first differences, let me see, my outputs were 1, 4, 9, and 16. So the difference is 9 and 16, 7, and then 5, and then 3. Well, my second differences are 2 and 2. So my second differences are constant, so that is a very clear indication that that is a quadratic expression. And the fact that we're saying something squared also very much tells me that is a quadratic expression. So the pattern that we're seeing here is definitely quadratic. All right, and I think, no, we'll go ahead and include this last bit here. No, I think we'll go ahead and let's just continue on. Let's just go ahead and finish this one off. Making a prediction. Sales of backpacks decreased over time. Well, here, how is the data? How is it correlated? What would we say the correlation of the data is? Now, in algebra, we have positive correlations, which kind of, you know, look like that, where they're going up from left to right. And we have negative, meaning that they kind of go down. And then we have no correlation at all, which just kind of looks something like that. So the data that we're seeing here is very clearly going down, so it has a negative correlation because it's decreasing as we go from left to right. Well, what conjecture could we write about that? So go ahead and pause the video when you're ready, write a conjecture, and come back when you're done and check mine out. So the conjecture that I'm writing is I'm saying, well, as the months go by from November to April, the sales of backpacks will decrease. Now this is where you guys, there's no really clear answer for this one. I want you to make a prediction. Make a prediction. How will we determine the number of backpacks sold in June? And does your prediction cause you to rethink your conjecture? So go ahead and pause the video and write your answer down, and when you're ready, come back. Now, my personal answer would probably say, I would probably say it's probably going to be still going down, but other people could very convincingly argue, well, I think that the number of backpacks might start going up. The number of sales might start increasing because, well, we're going to be talking about going back to school shopping at some point. So maybe they don't quite go up so much in June, but maybe they start leveling off from what you see in April and May. And obviously in July and August, those sales are probably going to start going up. So just because they're decreasing now doesn't mean they're going to stay decreasing forever. Now, the last thing we're going to talk about in this lesson is not so much about inductive reasoning. We're not looking at a pattern now. We're starting to talk about statements. And one of the things that you as a geometry student need to understand about statements is when statements are considered true and when statements are considered false. True statements have to be true 100% of the time. False statements exist anytime I can produce at least a single counterexample. So you might have a statement that's true 99.9% of the time, but that 1.1% of the time, that one statement that goes against it, and legitimately goes against it, causes the entire statement to be considered a false statement. So here are statements that generally we could think of as true, but there is going to be something that causes it to have a false category placed on it because there's a counterexample that we can come up with it. The first one should be pretty obvious. If a name of the month starts with the letter J, it's a summer month. Well, clearly January starts with a J, and it is not a summer month. You can connect any 3 points to form a triangle. Sure you can, unless the 3 points are on the same line. And when you multiply a number by 2, the product is greater than the original. Well, it could, but it doesn't always. What if the numbers are negative? Or what if the numbers are fractions? Or what if the number is 0? So those don't really work. So what I'd like you to do, again, make your own conjecture. Try to come up with one that is true, and try to come up with one that's false. And if it's false, provide a counterexample as why. So that is really going to take it, or that's going to complete the lesson here for our introduction into inductive reasoning. And from here, we're going to start getting into talking about this more, this idea of true false a little bit more with certain types of statements, which will lead us into deductive reasoning, which will lead us into being able to write definitions that we're going to be using for the remainder of the course. But until next time, guys, any questions that you have, again, make sure you email them to me, leave them in the comments for me to respond back to you. and I'll be happy to work with you on whatever issues you might have come up with this. And until next time, guys, thanks for watching. See you soon.